Okay, so today is Wednesday the 28th, and today, this is ECE641, model-based imaging, and today we're going to finish up the plug-and-play stuff. Friday we have the exam, which plug-and-play will be on the exam, okay? And this evening we're going to do a help session. And on Monday, we basically didn't capture a lecture because there were a bunch of questions and things, and it kind of didn't work out. So, but for the people in TV land, we'll make the help session this evening. I'll record it and post it, and if there's any questions. One of the big things that came up on Monday that sort of diverted the class a little bit in a good way was some of the software issues. So I thought I'd start off, if there should be enough time for the lecture, to go quickly over some of the software issues associated with some of the labs. And also, I feel like more and more I need to play the role of providing I can't even think of the word, mentorship or sort of guidance, spiritual guidance, okay? I have to provide spiritual guidance on coding issues, okay? Because coding is really important, okay? So it's not enough. I mean, you'd say, well, what's the most important? Do I need to learn the algorithms and the mathematics, or understand the application, or understand how to do the coding? And the answer is yes, okay? And you'd say, well, that's not fair. I mean, like, the experimentalists don't have to do all this stuff. Well, maybe they do, actually, but that's a separate matter. But you go, well, life isn't fair, okay? Okay, and whoever said life was fair? You got to be able to do it all, okay? We live in a highly competitive world, right? It's a global community, or whatever you want to call it. And, so if you want to be on the cutting edge, you need to be able to do all this stuff. And also, from a pragmatic, or perhaps, I don't know, selfish, I'll just call it pragmatic. From a pragmatic point of view, if you're looking to get a job, where you make money, and also where you have a fulfilling career, this is what employers are looking for. People who can do all this stuff. They want people who can do it all, who can, walk and chew gum, as it were, although I guess the walking and the chewing gum are pretty advanced. So it's really important that you that you learn about the culture of modern coding. It's not just a matter of writing a piece of code that works, okay? It's also a matter of writing it in a way that is compliant with social standards, okay? So it'd be like if someone came to dinner, okay, and they were eating their food like this, and it was like, it was like some kind of medieval thing where there was like all slobbering. You'd be like, oh my goodness, this person was never taught basic manners, okay? Well, there's manners in how people write code, right? There's sort of convention, and you're expected to follow that, or at least know it, so that you can interact smoothly with the rest of the community, okay? So I feel like I have to teach some of that, or at least, if not teach it, because frankly, I'm not sure I'm that good at it myself. In that sense, I guess I'm, I say one thing and do another. Okay, but I'm old. It's too late for me, okay? You're young, okay? So you need to learn how to code properly, okay? I used to code well in my younger days. I try to do what I can, okay? But it's, it's easier for you guys because, yeah. Anyway, the point is, yeah, it's very important. So the number one thing is to understand that it's important. the details of how you do it change, okay? But the most important thing is to understand and respect the fact that it's important, because it's how you interact with the rest of the technical community. It's one of the ways. So, you know, you write papers, that's one thing, okay? Some of you will continue to write papers. Some of you, if you go in the industry, may not do that so much that. You may have technical communications in a different form. But, you know, coding is another way in which you interact with the community, and you need to learn those standards, okay? And maybe I'm telling you something you already know. How many people feel, be honest, how many people feel like I'm telling you something you already know? Or that, how many people feel like coding gets discussed in their classes? Boy, like nobody puts up their hand. Not really, okay. Interesting, okay. So, yeah, I'm not sure we do the best job of this sort of thing. So at the last, what am I doing here? Here, someplace, teaching, 641. At the last lecture, we ended up getting diverted into discussing some issues having to do with implementation of the labs. So I wanted to go over that. So this is the lab. So some of the code was problematic, you might say. Oh, what's going on here? This can't be right. Oh, there we go. Ah, okay, good. Reload the page, because obviously. Okay, so I replaced these C code routines here. So if you click on this, it takes you to GitHub, okay? How many people here use GitHub? Everybody, or some people? A little bit? Okay, maybe everybody knows it. I just want to point out that, okay, so now what you do is you can, and I'm not very good at this, okay? But one way you can interact with it is you hit this GitHub desktop, because the actual GitHub is a repository that implements Git. So that just downloaded the code. And then this is a user interface. And this is what's called a revision control system, okay? So you can roll back when you make errors, in theory. I'm not that good at it, but some people are real Jedi Knights of Git, okay? And then they do it all from the command line. But I use this simple interface. But notice I organize, because this is one thing I've noticed, that people don't organize their code properly. So, okay, so it's this way that, first of all, ASCII code is still really important, okay? In fact, maybe it's more important than it's ever been before. So all these fancy GUIs well, the GUIs are nice for managing the ASCII code, but amazingly enough, ASCII code is as important as it's ever been before, okay? Everybody knows what ASCII means, right? Okay, ASCII is like the encoding from 8 bits to the alphabet, basically. So ASCII coding, and there's sort of ways you're expected to organize your code, like SRCs where you put the source code, right? And the conventions are different. This is for C. For Python, it might be a little different, but still people put they put the ASCII code in a directory usually called SRC, and then bin is the binaries. Those are the actual executables, and other things are more optional. So, and then, I mean, you can do all this stuff on the Windows too. I don't want to offend anybody who's a Windows fan, but whatchamacallit, Mac is basically, okay, hold on, what am I doing there? Okay, yeah. The Mac is Unix. The Apple's Unix. And of course, Linux is Unix. And Windows is a little different. But you can get utilities and for under Windows too. And let's see. So there it is. You can see I downloaded the thing, and there's a thing called C code. So I can CD into C code. Oh. And you know, learning some basic Unix is important. And then you CD into the source, and then, okay, this is the idea of, I don't know if they're going to be able to see that. Oh, probably. And then let me see if I can zoom in some more. Is that getting bigger? Okay. So that's what's in the source directory. And then there's a thing called a make file here. And the make file tells you how to compile things. And I updated that because the make file had some issues. I updated it to use, I guess C99 is sort of the most commonly used implementation of an ANSI C compiler these days. And then wall means make sure you apply all warnings. I really like warnings because warnings, if you fix them, it may seem like a waste of time because it compiled, but you know, a couple minutes spent fixing a warning by retyping a variable will save you a lot of misery down the road, because if you get rid of the warnings that are just not consequential, then the warnings that are left may be like basically clues that allow you to find really horrible bugs that will kill, you know, you'll be like pulling multiple all-nighters fixing some silly bug, which in the end is just like one thing, that some silly command that you put in incorrectly or something. So when you're working with C code, you want to be very risk adverse, okay? And make sure you're super careful and follow really careful conventions. And that's why I put pedantic in there, because it's like enforces compliance to the compiler. That way, the code will be much more portable. You can move it between platforms and it will compile. And then things like this basically tells you these are your object files, so Make knows how to compile things. Okay, you give it the flags for the compiler, and then this tells you all means it's going to build these two things, and clean means it'll get rid of all this junk. Okay, clean will only happen if you ask for it, and then this tells you how to this tells it Make how to compile. And it'll move the compiled things to the bin directory where you can execute them. Okay? So if I say make clean, well, it's clean already, so there's nothing to do. So it gives you some warning messages. But if I type make, then it compiles everything. Okay? And of course, it's super simple because I tested it in advance. Okay? And then it put the, if I go into bin, it put the executables in here. So notice there are little stars after there. That's because I have my ls, actually, which ls? I forget what the command is. Oh no, okay, I think I have alias. Yeah, okay, alias to ls minus f. So what it does is it always it puts a little star there to tell me that these are flagged. These are flagged as executable. If I look at the mode, so if I type ls minus l, these things here in Unix tell you about the read-write permissions. The first three are the user. Then the next three are the group. Then the last three are the, first three are all, I forget. Okay, is it user, group, and then all? But then there's one extra one, and it's for the executable, it's for whether the directory can be executed, I think. I forget. You can look it up. But this basically tells you the read, the permissions access for the files. And if it's X, that means it's executable. So this can be executed by me. So that's why I put a star there. And then I have demo. And then the SH is a shell. So this is a bash shell. So if I edit this, oh, you notice I use VI? That really dates me, okay? There'll probably be people out there rolling in laughter, okay? Okay, but I like VI. The bad thing about VI is that it causes your fingers to hurt because of the particular selection of which keys you have to hit. But the nice thing is that it's you get a very raw, unfiltered view of reality. So this first command here says to execute this shell as a bash shell, because there are different kinds of shells. The shell is the actual interpreter that you're interacting with when you use a Unix computer. So there are bash shells you can get for other operating systems like Windows, right? So you can get a bash shell for Windows, right? Yes. Yeah. But it tends to be associated with Unix. And this is running the executable. I could have added it to my path, but I didn't. I thought this is simpler. And then okay, we'll see that this thing generates an output called green in color, and then it puts it into the output directory. And then this is the B tilde thing. The B tilde thing actually, if you look at the main program for B tilde example, it actually, I created two routines, one for the B tilde and the other one for the potential function row. So if you, I think I can do this. Okay, I can't. Plot data, I'll let you do that. Plot data is a MATLAB script, but I don't have MATLAB on this machine. So it plots the output. It plots the output generated. Oh, I forgot to run this. So I source demo. Okay, so I ran it. Now I go to output. And you can see there's a TIFF file. If I go over here, I guess I can go look at it. Documents, GitHub, GitHub, C code, demo, output. So that's the one image that I kind of, it's just an example. I think you may have looked at it where it just swapped some colors. So that, and then there's supposed to be, that's the green channel with some noise. But then this data file, this is basically plots. The first column is delta. The second column is like the surrogate function, and the third column is the whatchamacallit, let me see if I can do this. The third column is the actual potential function. Hold on. Maybe I can do it like this. Okay. Convert to the oh. Okay, so I copied the data over to Unix where I can run MATLAB. And I say Oh, I need, oh, hold on, I see what I'm doing. This is, never mind. Oh. Let's see if this works. Plot data. There it goes. Oh my God. Okay, so you can see this is the actual potential function, right? And that's the surrogate. And I think I put the point of approximation at 2. So it's tangent at that point. So you can run this and see it, okay? So this is proof that the routines actually work. All right. I don't know if any questions about that? Was that useful? Okay. All right. Okay. Oh, why am I? Well, okay. Good. Okay. Now, I want to finish up with the plug and play stuff. Okay, so, we have that. Okay. So we're solving. So we are solving the problem. So we have f of v is equal to the arg min over x of f of x plus 1 over 2 sigma squared x minus v squared. Okay, and then we have h of v. This is a denoiser trained for removing additive white Gaussian noise with sigma, with variance sigma squared n, sigma n squared. And sigma n squared is going to be beta times sigma squared. All right? And then this becomes, beta is the regularization parameter. Does that look correct from last time? Anybody have the notes from last time? Because I'm doing this from memory. And I'd hate to have the wrong thing, because that would cause massive confusion in the future. But I think that's correct, right? So then equilibrium equations are f of x plus u, or I'm sorry, x minus u equals x. I'll put a star here because this has to be the solution, okay? And x star equals h of x plus u star. But I don't know. The stars are, there's just a lot of stars, and I don't feel like they contribute that much. So we'll understand here, x is, we're solving, we have to solve for. I'll put solve for xu. You solve for xu, but you really only care about x, okay? Okay, so how? So how are we going to do this? Well, we can use the ADMM algorithm, okay? But I want to introduce a more general framework. So, I guess I sort of talked about this. So maybe what I'll do is, we'll skip ahead because this is it, okay? So what we can do here is we'll say more generally, I'll put a dot, 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 okay? We put that f of w, maybe, so I can say here that we can have, we'll put here change of variables. We get w1 equals x plus x minus u, and w2 equals x plus u. Okay. In that case, the equations we get are that w1 plus w2 over 2 is equal to f of w1. And w1 plus w2 over 2 is equal to h of w2. Okay? So it's the same equations. I just want to make this clear because I'm now going to switch to the w notation. Right? Okay, so what we'll have is, more generally, we can have w equals w1 through w k. Okay? w1 through wk. And that, okay, and then, yeah, then what happens is that we define g of w, right? So, okay, well, okay. And then what will happen is that x star, or x hat, our solution, is going to be equal to the sum from I equals 1 to n of wi times 1 over n. Oh. 1 over k. Okay. And this is the same thing as that, right? Because this is just a special case. This thing here is x, because this is x, right? So everybody's okay with this? Does that make sense? Okay, so that's true. And what's going to happen then is that, okay, let me not call that, I'll just call this x bar, because the w's may not be the, I'm trying to drop the stars because I feel like the stars just make everything more complicated. But the w's may be at the optimum solution, or they may not be, okay? So in more generally, that would be just x bar. So then we have g of w is equal to x bar dot 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 x bar. In other words, it's just a bunch of, they're all the same, okay? And the x bar, again, is just 1 over k times the sum from I equals 1 to k of wi, okay? Right? And then what ends up happening is that the f of w is equal to f1 of w1 through fk of wk. So each of these things is what I like to call an agent. They're something that, they're a function that applies. Now the important thing is that let's say that Wi is a member of R, I don't know, N, okay? Then remember that Fi is a mapping from Rn to Rn. So this is a subtle issue. It's like a super subtle issue because usually when we're thinking about inverse problems or when we're talking about problems, the thing we're interested in is the function that takes the data and gives us an answer, okay? So remember, data in this class is y. I try to be pretty consistent about that. So it's a function from y to x. That's usually what we're interested in, but that's not what these are. These don't take the data and produce a solution. Now, of course, some of them may use data as input, but it's suppressed in the notation. Sort of the big idea of a proximal map or of these agents is that it's like you, does everybody know what Gestalt is in psychology? It's like where you see like a bunch of blocks and you blink your eyes and then the blocks reverse. Or you see like a person and then it switches and it's a woman or something like that. Or like a lampshade turns into something else. Do you know what I'm talking about? That's called the Gestalt Effect. It was a famous psychologist. And so it's all how you look at it, okay? Okay, it's all your point of view, okay? So, yeah, sure, so you're taking the data and you're making a reconstruction, but that's not, when you take a proximal map, it's sort of like you change your point of view. Your point of view then is that the input isn't the data, even though that's obviously an input. You're thinking of the function more as its input is a reconstruction, and its output is a better reconstruction, okay? So f of I of x equals, so goes to x prime, say, I don't know, x. So this is a reconstruction and this is a better reconstruction. So F uses the data. Sometimes, obviously, so I'll put here Fi of x, and I'll put a semicolon y here sometimes. Because it's obvious, we suppress the dependency on y, even though it has to depend on y. We think of the data for your problem as constant, okay? And because we really want to emphasize the dependency on, you give it a reconstruction, and it gives you a better reconstruction. That's a very natural idea, because in iterative reconstruction, and these iterative optimization problems, you're always taking something and making it better, right? That's sort of the idea. It's like okay. And the key, and something that's really interesting is that y is in a different space than x. But here, the input and outputs are in the same space. The advantage of them being in the same space is it's easier to formulate a solution. You can't have a fixed point solution if the input and output are in different spaces. The whole idea of a fixed point is that the input and the output are in the same space, and somehow you reach a point where the input and the output are the same. The input and the output can't be the same if they're in different spaces. So you can't, in order to formulate this as a solution to a fixed point operator, you have to be thinking of the input and output and being in the same space. Okay, it's a subtle point, but I think it's important. Okay, so this is an important point. So here, the input and the output are in the same space. Yeah?
But the data can be a different dimension, yeah, for like compressed sensing or something like that.
But that's the y.
But the y can be a different dimension.
Yes, but the y is suppressed in this notation. So that's important to keep in mind. Okay? obviously it's there because you can't do anything without data, okay? Okay, now, so I'm going to erase this because it's, even though it's important, it's been said. And I want to keep the other stuff on the blackboard. Okay, so then what I call the, so the equation becomes f of w equals g of w. Okay, and I call this MACE, okay? Okay, that's what I call it. You're welcome to call it something else if you prefer. But this is the equation, okay? And some notes. When Fi are proximal maps, then x hat equals the arg min over x of the sum over I equals 1 to k of fi of x is equal to 1 over k times the sum from I equals 1 to k of wi star. I'll put a star there to emphasize that it's the solution to the equation. I guess I'll put a star here. I hate using the stars because I feel like they obscure things, but I'll put the stars here to make it clear, okay? So this may look like a bunch of gobbledygook equations, okay? So what happens is if all the f's are proximal maps, then each one corresponds to some cost function, and the solution to this equation is equivalent to minimizing the cost functions, the sum of the cost functions, okay? And you get the, but of course, solving this equation isn't the answer. You have to then do a little bit more. So you solve this because it gives you a bunch of these states, but the states are all different. And then what you do is you compute the average of the states. That's the actual output. But remember that, so this thing here is what we call W bar, I guess, or X bar, I don't know. Okay, I should call it X bar, I guess. Okay, but it, or W bar, I don't know. But it's the output of all the G's anyway, so, you know. Is everybody clear on that? Okay, now, so equivalent to 2f minus I times 2g minus I times w equals w, okay? I derived that, so I won't derive it again, and we'll call this t, okay? So then the iteration, I'm allowed to erase this now, right? Because this we've done. So the iteration then becomes repeat. Okay, man iteration, repeat, x, okay, say w goes to w, so, you know, w init. Or I'll just put init w, okay? You know what that means. Initialize it, however you like. You can make it 0, whatever. Often for real problems, there's some kind of initial guess, which is pretty reasonable. Like there might be some classic algorithm, like in tomography it would be filtered back projection. In other algorithms, there's some kind of way that is like the 0th order way or the 1st order way of computing a solution. So do it, okay? Then what you do is you say W goes to, I have to make sure I do this according to the correct convention, times W rho plus 1 minus rho times T of W. Okay, which t is actually 2g minus I times 2f minus I. By the way, you can actually flip these, and it sort of doesn't matter. By sort of, I mean, if you can solve it this way or the other way, it still works out the same. It's just the way you compute the answer. The way you read out the answer is slightly different. But I'll go with this because it's more intuitive. And then you just do that, okay? Now, although, you know, this is okay, but there's a different way of writing it down, which repeats that I kind of like better for some reason. You go x goes to f of w, z goes to g of 2x minus w, and then w goes to w plus 2 rho z minus x. These are algebraically equivalent, but I think this is an easier way to implement it. At the very least, it like deconvolves all this junk, which you can't typically. Mathematically, this is fine, but if you're writing a code, then, you know, it's not easy. I mean, the compiler can't figure out what you mean if you write this. Okay, whereas if you write this, the compiler knows what you mean. So this is easier to code, I guess, is basically what it comes down to. And this is notes, converges when t is non-expansive and rho is in the interval 0 to 1. 2 is that when fi are proximal maps t, then t is non-expansive. Okay? So if in the special case where they're proximal maps, then it converges. It turns out to be a slight generalization in the ADMM algorithm because it's exactly, oh, no, I'm lying slightly, okay. When rho equals 0.5, then this is what's called consensus ADMM. There's a variation on ADMM which is called consensus ADMM. Okay, so, and then these are kind of parallel operations. Now, the intuition here is this, that what you're looking for is you're looking for a solution where you have a bunch of inputs. Okay, you have W1, W2, W3, W4, okay? And each of these, this would be like F3 of W3, and this is F2 of W2, and this is F1 of W1, and this is F4 of W4, okay? So these are, I like to think of them as people, so I call them agents, because to me it's more intuitive if you think of them as people, okay? So here you have a person, you give them a solution, they go, well, that solution's fine, but I'd like it a little better if it was this, okay? And this solution's good, but can we reduce the cost? And this solution's great, but I'd really like to make the product a little better. There was a time when Purdue had 16 vice presidents, okay? So they can think of these as each as the vice president. I don't know. How many is the optimum number of vice presidents for the university? Maybe we can pose that question. The advantage of having more vice presidents is that as the number of vice presidents go to infinity, then each of them becomes completely useless. So then you don't have to interact with any of them. So it's kind of a trade-off. Probably it's better to either have 0 or infinity. But so it's like each vice president is moving the thing in some kind of direction. And then they all agree on the outcome. But you get them to agree by giving them an input which is sort of not what they wanted. Because if you gave them this input, they would all sort of diverge. So you give them each an input that's sort of pulling against what they want to do, right? And then they move it to the same point. They go, oh, we all agree, okay? But then also, you have the other constraint, which is this thing is x, right? You have the other constraint, and then x, I'll call it x hat, or I don't know, x star. That's x star. You have the other constraint that x star is equal to 1 over 4, the sum from I equals 1 to 4 of wi. So we really have two sets of constraints. The one constraint says that each agent moves from their given input to the output, and then they all are the same. But also that if you take all the inputs, they average out to do the same thing. So when you do both those things, then you've met the constraint. Okay? And so that's kind of nice. I don't know that there's a whole lot more to say on that. But we're just out of time anyway, so I don't know if there are any additional questions. If not, I think we're basically finished. Yeah?
I guess, is this the same thing as, I guess my question might be a bit like nuanced, but the idea is that, say, f1 to fk is the gradient of some other function that you'd like to optimize over. And then it looks like maybe this algorithm is the same thing as gradient descent.
It's very closely related. That's an excellent question. It's intimately related to gradient descent when the things are proximal maps. Oh, so one of the things that's important to point out is I kept forgetting to say it. No. When fi are not all, okay, all, because they have to all be proximal maps. Proximal maps. Which means if any of them are not proximal maps, okay, then x star is not, I'll put here, sort of, because what I'm saying here is not technically correct, okay? It's sort of emotionally correct, okay? Is not, in a sort of sense, the solution to an optimization problem. So in other words, you're not solving a problem where you're computing, setting the gradient of a function equal to 0, where the function is conservative. Okay, it's not the gradient of a function. Okay, the thing you're zeroing out is not the gradient of a function. You can always cook up a problem where the solution, where this is the minimum of some optimization, but it doesn't capture the idea. So the point is that, well, okay, but when fi are proximal maps, Then, dot, dot, dot. Well, here's the thing that's interesting. If you have f I of x, okay, and then sigma squared. Sigma squared is the parameter of the proximal map. Okay, then this thing is approximately equal to, and I hope I get this right, it's going to approximately equal to x minus sigma squared times the gradient of f of x. So asymptotically, as sigma goes to 0, this proximal map behaves like a gradient, sort of like a gradient. It's not the gradient. It's the gradient. It's sort of like a step of gradient descent, asymptotically, for small sigma. So yes, it does have an interpretation that's similar to gradient descent, and that's why. But the result that the solution is the solution to the optimization problem holds even for large sigma. So it's not constrained. But asymptotically, as sigma goes to small, it looks like you're doing gradient descent, essentially. Yeah. Anything else? Okay, great. And then we're going to have a help session tonight at 7. And I'll see you then. And then make sure you're preparing for the exam and you got the emails with all the homework solutions in them. You should go through all those and at the very least copy them over and hand in the homeworks, okay? All right. See you later. Bye.